All right, yeah, so to review from last time, we're going to have a recursive function here, or method, pardon me. But we've got that public-facing one that just calls the recursive one with the initial conditions we need to run the recursive method. And then what do we have? Well, it's just a search through a binary search tree. It's a search through a binary tree, a binary search tree too. Takes a node, the thing we're looking for. If the current node is null, well, it's not there. It's kind of like, that would be the same thing to like getting to the end of the list and it's not there. Okay. But of course, this is not a linear structure, it's got two. So if it's not that way, maybe it's that way, right? So if the node's not there, we haven't found it that way at least. And then we do an object contains, well, if we found it in the node, then we found it. Otherwise, continue looking left and right. Okay? So if we have a tree, a very simple tree, let's say, who cares what's over here? Actually, no, let's do it this way, where there's null here and some arbitrary large tree here. Again, I'm representing large arbitrary trees, subtrees here as like triangles. In a situation like this, I go like, okay, does this contain the thing I'm looking for? If it does, great. If not, we'll continue searching over here. Oh, there's nothing there. So could it be there? No. All right, search over here now. And so on and so on and so on. That's the idea, right? It showed the null, the case, and whatever, right? As soon as we find it, we can return true. And then like if we had like, let's say like the left, this returned false, because we never found it during the left subtree, but this returned true, well then this false or true, it's true, we found it. But obviously this is a very, I mean, there's nothing wrong with this, but it's not taking advantage of the binary search tree's property. The fact that if I'm looking for a number, and I know the number should be over here, I don't need to look over here. That's a waste of time. So, how do we do that? Well, same idea, but now we've got a slight variation. I'm saying, okay, the thing, if it's not there, it's not there. Do the comparison. I took the comparison out, and I'm just saving the result. And remember, we're using compare to. Compare to gives you 0 if they're equal, -1 if this thing is less than that thing, and +1 if this thing is greater than that thing, right? And it's important to keep track of what's being compared to what here to know which direction to go. But if the comparison's 0, we found it. Otherwise, if comparison is greater than 0, that means the current is, do I have that right? Current, the element. Current node. If the current node is greater than the thing I'm looking for, the thing I'm looking for must be to the left. So do the search on the left. Otherwise, do it on the right. Okay, so when we start to analyze this thing, how does it differ from the other search? Well, the other search is, no matter what, we could have the 2 recursive calls. Sure, we've got the short-circuiting situation, but in general, each call to this method will call it 2 more times. Or no times, but for each call, it calls it twice. And remember, we talked about this before. Why is that not exponential growth? Each time it calls 2, in which those each call 2, so there's 4, and each of those call 2, so it's 8, and so on and so on. Why wasn't it like that? Well, it would be like that if we were thinking of like h, the height, but we're not thinking of the height. We're thinking of the number of nodes in the tree. And intuitively, if there's n nodes in the tree and we want to look at each node, we look at each node, right? So n, right? But that whole exponential growth thing that we saw with Fibonacci, why is it not here? Well, it's all about that relationship between the height and the number of nodes. As the height grows bigger in the tree, the number of nodes grows exponentially. But the number of nodes is the number of nodes, right? Yeah. As the number of nodes grow in the tree, the height grows logarithmically. If you're like, wait, what? Log and exponential are the inverse of each other. Like plus and minus, multiplication and divide, and so on. So with this one, though, at most, we will have 1 recursive call, right? At most. Because we're either going to run this one or this one. If else, they're mutually exclusive. You will never call both. You will ever call one. So what's the computational complexity of this? If I have n nodes in the tree, clearly I'm not going to search n nodes because I'm only ever going to search one side, right? There's n nodes divvied between here, here, and this one, right? One sec. If I'm looking over here, I'm not looking at these ones. I'm looking at these ones, okay? So I'm not going to look at all n nodes because all of this is n. If I'm only looking at a subset, I'm looking at some amount that's probably smaller than n. So it's not going to be linear. Although also too, when you look at a tree, let me put it this way. What is the furthest this could ever go? The height. The furthest this could ever go,
the height
plus 1 because you'd go down and be like, it's not there. It's not there. Yeah, but who cares?
Well, you also have to check the top.
Yeah.
So the height wouldn't include
Okay, fine.
Yeah,
Yes, you're right. Absolutely. But the furthest you'd ever go is like one path down to a root, or to the leaf from the root. That's the furthest you could ever go. Because you go, do I want to go left or right? Left or right? Left or right? Left or... And the furthest you could ever go is the height of the whole tree, the longest possible path. That's the worst case scenario. So the worst case scenario is the height of the tree. So like, what's the computational complexity here? Well, I mean, we kind of showed it, right? It's like, well, it's linear relative to the height of the tree, which would be what relative to the number of nodes in the tree? Log. And if you're like, what? Why? Well, first of all, let's make it clear. Why would it be linear based on the height? Well, the furthest it could go is the whole way down. Pretend this is the path that it would have gone. I'm looking for the number 9 or 10, I guess, as well. It's not there. But if I'm looking for the number 9, if 9 is in this tree, it must be to the left, must be greater than, must be less than, and so on. We found it. So there's like a place where it would be. And if you ignore the other calls, it's just a linear structure. Obviously, it's not. But along the path that it was, there was only one possible path. There was no decision. There was no branching, really, on our search. So it's linear there. And if the height of the tree is like x, well, the number of things you'd have to look at is, worst case scenario, all of them, right? So it's linear based on the height. So it's like order h, I guess, where h is the height, right? But if I ask you, why, like, what is it relative to n? Well, I would say that's big O of log base 2 of n, right? And well, why? Well, there's a couple of reasons why that we can kind of like use our intuition to tell us. First of all, we know that the relationship between the number of nodes and the height of the tree is exponential logarithmic, right? We already know that, right? So there's obviously part of it there. But the other part of it is every time, now this actually requires a bit of an assumption. This requires a nice balanced tree, which we will talk about shortly. But if every decision, I'm going to hopefully half the remaining things, right? Think of that. Pick a number between 1 and 100, right? So who wants to volunteer? Perfect. Pick a number between 1 and 100. Don't tell me. Tell me when you got it, though. You got it. Is it 50? Is it higher or lower, though? Higher. So I know it's between 51 and 100, right? And I've eliminated all numbers less than. So I've eliminated like half the things. Is it 75? Lower. So I now know it's somewhere between 51 and 74, right? And I've eliminated, so the first guess, I eliminated the numbers 1 through 50. That was half of what was there, the 1 to 100. The second guess, I eliminated half of what was remaining, right? Remaining, there were 50 numbers, 50-ish, 50 to 100, but I made a guess and I eliminated 25, half of them. And the next guess would eliminate 12 and so on and so on and so on. So every guess I eliminate half. And if you half and half and half, if you keep dividing by 2, divide by 2, divide by 2, divide by 2, if you keep applying division over and over and over, that's log. That's what that is. It's the opposite of doing multiplication over and over and over, which is a power, right? Exponential, sorry. Yeah. You did have your hand up a moment ago, though. That was like several moments ago. Oh, okay, perfect. So there are a couple of ways we can think about this. But that does require that our tree is balanced. But more on that shortly. Any questions about that binary search thing? Okay, right? Binary search tree operations. This was just explaining what we just did, right? Like, let's say we look for 22 in this tree. Is 14 22? No, but it's greater than it, so it should be over here. Is 26 22? No, but 22 is less than, so if it does exist, it must be in the left subtree. Is 19 22? No, but if it does exist, it would be to the right of 19. Is 23 22? No, but if 22 does exist, it'd be to the left subtree. Oh, nothing, it's not there, done, it's not there, right? Because where else could have 22 have been in this tree? Literally nowhere else. Unless the tree had a different shape, but that's a different question. Pardon? It was a different tree, exactly. Now, following that idea, if I wanted to add the number 22, where must it go? Exactly. If I wanted to add the number 11, where must it go? See how, like, where do you add something? There's an answer, right? Now, let's say I say add the number, where did we just add 22? 22 must go, it would go here, right? But let's say I say add the number 20. Where would it go? Same spot. Then add 22. It would go there now. So the order that we add things matters, obviously. But at any instant, when I say add a number, there's an answer. So what would adding look like for a binary search tree? Well, it's effectively a binary search to find where should it be and then put it there. So what do? Define add. Okay, if the node does not exist, insert the new node here with the element to be added. So that would be like, imagine there's an empty tree. Oh, perfect, goes here, right? But here's where recursion comes in, right? You look at the left subtree. What if the left subtree is null? Oh, perfect, add it, and so on, right? So if the current node doesn't exist, add it there. If the node does exist, if the element is less than, add it to the left subtree. Where? I don't know, but call this add function and it'll figure it out, or method. I've been mixing up my method and function a lot. Otherwise, if the node is greater than or equal to, add it to the right. And this recursively goes. The only difference here, instead of returning true or false, it just adds it. So yeah, add the number 13. Where does it go? Well, this one makes it pretty obvious. It shows you, right? So if we had an empty tree and I said add 26, where does it go? Right there. Add the number 15. Where would it go? Well, it must go there. 38 must go there. 31 must go there. Add 7. Where must it go? To the left of 15. Perfect. 34. Where must it go? Right there, and so on. There's an answer to where does it belong. So that's the idea. Min, max, or min and remove min. Well, finding the minimum number in a tree is fairly easy. Remember what we saw with a binary search tree, pardon me, is fairly easy. What do? Go to the left until you can't anymore. There, you found the smallest thing. What about finding the biggest? Go to the right until you can't anymore. You found the biggest, right? And again, if you're like, how is that true? This is a binary search tree. If there was a number that was bigger, if you go to the right, all the way to the right, and you're looking at a node and there's no more right child, I am saying that that number must be the biggest number there is. And you say, how do I know? And I say, because if there was a bigger number, and this is in fact a binary search tree, which it is, if there was a bigger number, it must exist in the right subtree of that node. But if there is no right subtree, there is therefore no number bigger. Make sense? Cool. The same would be true forever, right? So if I go here, now how about removing the min, right? So let's say I go here. I mean, we got a couple of cases actually, right? So we can find the minimum node, and all of this is going to be true for the maximum, just flip it. we can find the minimum node, but there are a couple of cases to consider. If I want to remove the minimum node is the root. Imagine that the minimum node in my tree is the root. That's possible, right? That's entirely possible. I could have a tree that looks like that, right? This is null. There's nothing there. It's the minimum node. Entirely possible. What do I do in that case? All right. What else? The leftmost node has no children. Okay, what do we do in that case? And then there's the third case. The leftmost node is an interior node. However, again, if it's an interior node and we're looking for the minimum, if it's an interior node, that means it has a right child, but not a left child. It can't possibly have left and right children. Why? Because then it wouldn't be the minimum. Because then there would be something to the left, right? Right. So finding the minimum is easy. Removing will be a little trickier since we have some potential children to take care of, right? So what do? And further, not only must the children stay in the tree, but the proper binary search tree ordering must be preserved. We can't just start moving things around willy-nilly because that might destroy the ordering of our tree. So we have to be careful. Like if I say here, remove the number 7, what do? Well, what makes the most sense here? Pardon? Yeah, just replace 7 with 9 is what you said, right? Yeah, okay, perfect. As you can clearly see there, right? Does that make sense though? Yeah, it makes perfect sense. Now if I say remove the minimum again and you're looking at that tree to the right, what would you do? It's a leaf node, so what do? Just remove it. No big deal. Great. Now 15 becomes the smallest. Great. Okay, so the leaf case is pretty easy. The case where you got a right child, that's not too bad, right? Right? You just promote it. Remove the minimum. Now I say, okay, remove 15. Okay, great. Now what do? Well, that's actually not too bad. You just kind of promote it, I guess, right? Right? What do? Well, just remove it and you promote the right side. In fact, it looks like every time there was whenever you had an internal node, the trick was always promote it. Just promote the right child up. That's it. But will that always work? Because what happens if we have a case that looks like this? And now, mind you, I'm just showing you this as an example. It's actually not too bad as we go. Imagine I have a case where I have I don't know, let's say 10, 5, perfect. 8, no, 7, 6, and let's say we have another 7 here because it's a repeat, right? And that's allowed. Can you see that? No, you can't see that half of it. Can you see that reasonably okay? So will that promotion still work? Because well, okay, that gets promoted up, but what about, is that really the next smallest thing? It doesn't have to be the next smallest. It doesn't need to be, this node doesn't need to become the minimum node in the tree. That's an important feature about this. Whatever is in here doesn't necessarily need to be the next minimum. If that gets promoted up, right, basically this happens, and everything's still fine. So we're actually in a pretty lucky case that if it's a leaf node, just get rid of it. If it's an internal node, all you have to do is promote the right subtree. And in fact, if you think about it, the strategy of promote the right subtree works if it's a leaf node too. Because what's the right subtree of a leaf node?
No.
Bingo. So actually, I talked about 3 special cases. It really kind of seems like there's really only one case. I mean, the cases are different, but the solution is always the same, conveniently. Although there might be some bookkeeping we have to do if it's the root, right? Fine. But in general, kind of a neat little thing there. So any questions about that? Yeah? Check if the children exist. Yeah, so the minimum value is the root node. This means that there's no left subtree. There may be a right subtree. Therefore, simply replace the root with the root of the right subtree, which may be null, but that's fine. The ordering in this particular case is preserved because nothing is to the left of the root. Everything to the right of the root is larger than the value in the root, right? The right subtree must be a binary search tree if this whole thing is a binary search tree. Therefore, the right subtree becomes a new root. The binary search tree's order is maintained because it is in and of itself a binary search tree. Right? Right? Makes sense? Makes sense. Case 2. If the minimum is a leaf node, this means that there's no children to deal with. Therefore, just remove the node. By eliminating only the leaf node, the ordering cannot possibly be affected. And then case 3, the minimum is an interior node. This means that the node has no left subtree. Otherwise, the node would not be the minimum of the tree. Right subtree does exist. Therefore, replace it with the node's right subtree's root. The node being removes parents, left child will become the node being removes right child. If that didn't make any sense, what I mean is, like in this case, this is the node being, let's say this is the node being removed. No, that's not possible. There. Let's say this is the node being removed. Remove me. This is the parent, right? So I'm saying the node to be removed's parent's left subtree becomes the node being removed's right subtree. Which sounds like a lot, but I think it should be, I know you can't see, I know. That might sound, the parent, the root, parent's left is the right. I know it sounds like crazy, but if you just draw it out, I think it's pretty darn simple and straightforward. By the way, and I've said this to a couple of you, one of the best, if you can, raise your hand if you're going to take more computer science. Good. One of the best investments you can make, and I recommend you make it now, is go and buy yourself a little whiteboard. And I didn't make this purchase until like I had to really deal with trees. And then I got the whiteboard, I'm like, everything, this is perfect. It was one of the best things. I still have it to this day. It's sitting in a closet. I don't use that one very much anymore, but it was really nice, good investment, highly recommend it. You'll save yourself a lot of paper. And it's a lot easier to, erase, mark. Anyways.
Or have something digital to do it on.
Yeah, I guess you and your kids these days and your fancy iPods and everything, yeah. Back in my day, we didn't have, that wasn't a thing.
Etch it directly in the stone.
Yeah, we did. I had I didn't have an iPod, but I had was it the iPod video? That was like the big generation for us. Pardon?
An abacus?
A what?
Abacus.
An abacus?
Oh.
Like an actual abacus. I thought you were like, oh, was there something called an abacus that wasn't, like, who made the abacus? Ancient man, yeah. All right, I gotcha. Anyways, where were we? The ordering is preserved in the same way, nothing to the left, same reason as like the root, right? So are all cases the same? Well, the solution to the cases are the same. The cases are, I suppose, different if you think about it, but the solution is the same. I guess the root's the weirdest one because the root doesn't have a parent, right? But basically you're replacing the node with its right subtree. That's what you're doing. And then max, the same thing, except instead of going left, we go right. And then instead of it having a right subtree, we have a left subtree. You just inverse everything, should be fine. What about a general remove? Remove the number 26 from this tree. Make two trees. Problem solved. I like the way you think. What do you mean this is a problem? There is no problem. Right? What do? Well, it's actually not too bad. It's not too bad of a thing. Because if I removed this, I need it to be replaced with something that preserves the ordering of this tree. Makes it still a binary search tree. What are you thinking?
The middle of the two.
The middle of the two children? The middle, like a middle. Oh, but that would be like adding a new number. We don't want to add a new number. What are you thinking?
We can make 15 and 26?
We could put 34.
30. Oh.
If we put 34 there,
What the
no, if we put 34 there, then 31's on the wrong side.
15?
What do you think back there? With your hand up? What are you thinking?
You can put any of the left or right up there.
What do you mean? Oh, we could promote either of these? Well, if I put a 38 there, we kind of have to rejig where 31 is a little bit. What are you thinking?
Promote either the largest of the left subtree or the smallest of the right subtree.
That makes good sense. That makes a lot of good sense. Why would that work? So let's restate what he said. What we could do is either go over here, and this is a small example, but we could go over here and find the biggest value in this subtree and put it in here. Or we could go over here and find the smallest value in this subtree and put it over here. Would that work? Yes. Why? Because if I find the smallest value in here, I will have a value that is at least, it might be the same, there might be equal values, but I guess for right now, let's assume all the numbers in here are unique, just for simplicity, okay? They don't need to be. But if I find the smallest number here, that means every number in here is bigger than it. So if I promote it, all the numbers in this subtree are still bigger than the number I just promoted. Obviously, we have some rejigging to do in terms of where things are. Like in this case, I guess 31 would have gotten promoted because it's the leftmost. But is the left subtree okay? Well, hold on. If the number is in the right subtree, it must be bigger than all the numbers in the left subtree. So it's safe. So we have one of two choices. We can either promote the biggest over here or the smallest over here. Yeah?
What do you do with the numbers below the one that you promoted?
Well, we're going to have to kind of, well, actually, if let's say we're removing the smallest in the right subtree, we already know how to remove some from the smallest thing from the right subtree, don't we? We just did that, didn't we? Look at that. Holy moly. It's almost like this was designed. So what do we do in that case? Yeah, so now we have a choice to make. Should we remove from the left or from the right? Which one would you do? Well, either will work.
Right.
The right? Why? Why?
No good reason.
No good reason. Can anyone else give me more method to the madness at least?
I mean, would it make it balanced?
Balanced.
Okay, balanced.
We have the size of each.
The size of each you want to, okay, so like intelligently pick which one's bigger, pull from them. That's interesting. But let's say you want to have just like a hard, fast rule. This is what we're doing. And give me good motivation why. Both are fine. But if I asked you on a test, now how would I word this? But I want you to give me a more satisfying answer. Yeah.
The left one because you have to search less because there's a limit to how small.
No? Okay. Can anyone give me like a good, I want someone to read my mind right now. Remember, in our definition, I'm going to give you a big hint. In our definition, we do allow duplicates. Where did they go? To the right. So we could replace the node with its same value, which, is that important? Really? But it's kind of nice. There's a niceness to it. So like, to me, this is an example of we have a design decision to make. We can go left, right. Both are fine. I got to pick one. Why pick one over the other? Here's why. Because it allows duplicates. Is it better? But at least I had method to the madness. Like there was justification, right? It's slightly less arbitrary of a decision. Does it matter though? No. It really doesn't, to be clear. But again, you know, I think I've emphasized this a lot this semester. When you have a choice to make, try to at least have a reason for making the choice. Like justify it to yourself.
I mean, sometimes you might fight a little bit too hard to make it
Absolutely. If an hour goes by and you're like, this, that, and you do it one way, then you undo it, and
This one was okay to be arbitrary.
yeah.
Like,
Anyways. So, okay, in the above example, there may not be an immediate, obvious, clear way to address this. So what do we do? Case one, if the node being removed is a leaf node, then simply remove it. Like if I said remove 7, goodbye. Remove 34. All right, goodbye. If the node being removed is an interior node, then things get hairy. Now, and by the way, don't get too confused here about me. That was the root of the tree. Every node is the root of some subtree. Don't forget that. All right, what do I say? Case 2, if the node being removed is an interior, we just worked through this. The biggest from over there or the smallest from over there. Below is an example. Initial tree, remove 70. Okay, that's easy. Just goodbye, right? Now, we're still kind of doing the, remove it with the smallest thing in its right subtree. Well, there's nothing there. All right, great. Null. Remove 7. What do we do? Remove it with the smallest thing in the right. Okay, 7, 9. There we go. Now remove 38. 38. Now 59. Ooh. Here I did something. Here I did the biggest thing in the left subtree. I'm just showing you that like this. We're not following the strategy I did. I'm just showing you how we could have done it with a 36, I guess. Although if it was kind of the 59 would have been nicer if it was me again. But still, it doesn't really matter. Remove 26, and so on and so on and so on. Oh, by the way, the contains, we are, we're talking, why is that there? Strange. All right. I don't know why I'm talking about, like the other day, so I always check, a way to check contains. Because we did that up there. I don't know why that, whatever. All right, by the way, I'm just thrown off why I'm like analyzing contains there, which is well after the fact that we talked about contains way up here. I don't know.
Would having the both method, like finding the larger on the left and this one on the right subtree be necessary? Because if you go up and on the remove 7,
Or this one.
If you have remove 7 from the number, it said to replace it with the number 9.
Yeah.
But if you go with like you have the larger number of the left subtree, it would like the 7 be replaced with null, and you lose 9.
It would, but I guess we have a special case here, right? Because we can't leave. There's a special case of like, well, what happens when we were removing the minimum? We never had to worry about a left subtree, right? So in that case, but we're not removing the minimum. We're doing a general purpose remove. And so we do have that other child to like take care of. So we got to be a little careful, right? So if there is no such thing as the biggest thing in the left subtree to put into here, that 9 kind of gets lost, I guess. Yeah. Anyways.
You want me to move that up?
I'll do it later. Don't worry about it. Because I'm trying to remember, like, was there a reason I put it there? Like the other day, always check the elements collection needed. Although the exhaustive depth first search through the tree would work. Yeah, it's weird. I'll think, like, I'll try to find out why it ended up where it did. 3 point.
Like, I feel like
26.3.
Like, I think 3.5 and 3.6 should both be moved up. It seems really weird.
I'll go through and like look and try to find out what I was doing. By the way, you've got a couple of open PRs that had responses you got to deal with. All right, what's going on? Counting the number of nodes in a tree. Did I have you guys do this? No. But we did, right? Counting would be like, well, how many are over here? How many over there? Plus 1. We did that in the previous topic.
Yeah, but this is of a
No, in the lab you did the height. Oh, you did? Oh, well, then you're fine.
But this isn't the total nodes. This is of a specific node.
Oh, yes, absolutely. Thank you for catching that. Yes. All right, so we just did a linear, we didn't just, we previously did the binary search. Now, if you want to count the number of nodes in a given binary search tree of a specific element, you're going to have to do some searching. Now, very quickly, if you think like, well, if I'm looking for the number 7 and there's duplicates, it must be down like this way, right? Not necessarily, right? Because depending on how things were added, if I say 7, add 8, add 7, add 7, right? Like it could get kind of out of whack. Long story short, you go like, is that the thing I'm looking for? Yeah, count it. No, go to the left or go to the right. But if it is what we're looking for, we still got to go down to the right because there might be duplicates. So I would go, let's say this is my tree and I'm saying looking for 7s. Is that what I'm looking for? Yes, count it. Go to the right. Is that what I'm looking for? No, go to the left because it's less than. Is that what I'm looking for? Yes, count it. Go to the right. Yes, count it. Go to the, and so on and so on and so on. So what would that look like? It's just basically a binary search tree, but instead of returning true or false, you return the count. But you got to go all the way down until you get to like a null. Until you get to like, if there was a 7, where should it be? Right? All the way down. But of course, yeah. Questions, thoughts, concerns, comments? Now, a lot of this analysis here depended on the tree being balanced. And a balanced tree is one where like, you've got like a good number, like an even-ish number on the left and the right subtree. Now, a balanced tree is a tree that has the properties such that the height of its left and right subtrees can differ by at most 1. Okay? And this must be true for all subtrees. Okay? Now, the tree on the left is balanced. Okay? All possible combinations, right, are, there's no more of a height difference anywhere of more than 1. That's fine. But something like this is not balanced because the height difference between this one's left and this one's right is more than 1. Okay? That's a problem. Well, problem isn't the right word, I suppose. That's a predicament. I don't know, an important feature. And it's an important feature because if it's balanced, we get those nice properties of like, if I'm doing a binary search, it's log n. Okay? But if I were to add the numbers 3, 5, 9, 12, 18, and 20 to my binary search tree, it looks like this in the end, right? We add 3, we add 5. Where's it go? There. 9, where's it go? There, 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 there. And I don't know about you, that doesn't look like a tree. And I don't know about you, but to me that's pretty obvious. How many nodes are in that tree? 6. If I did this with n numbers and I happen to add them in order, how long would that tree be? What would the height of that tree be? Yeah. Well, who cares? N and H would be the same. There wouldn't be a property between the height and nodes like it would be if it was balanced. The height and the number of nodes, right? Where the height is the number of nodes. So now if you were to do like a binary search through this, it would always be linear.
Not very binary.
No, it wouldn't be very binary at all because there's nothing to the left or the right. So we got to be careful. This is called degenerate. It's a degenerate binary tree, right? Now that is a very extreme case. It's effectively a linear data structure, not a tree. So consider the binary search tree, or a binary tree. With a balanced tree, the left and right are going to have roughly the same number of nodes in it. They might not have the same number of nodes because you're allowed to have like a difference in height a little bit. But the balancedness is where we get that, the whole feature, right? If it wasn't balanced, right, like the whole idea is, like when I said pick a number between 1 and 100, and I said, by going left, I want to eliminate about half. It can only be half if there's like the same number over here and the same number over here, and so on. In that case, every time I'm looking for the number 77. Like I'm not eliminating half. I'm eliminating one thing, the root, the whole way. That sucks. All right. With the degenerate tree, it's basically linear data structure, all elements, yeah, whatever. So there do exist strategies for, there does exist strategies for making sure our trees are balanced. Basically, whenever you add or remove something, it does a check. and it says, did I make my tree not balanced? And if you do a couple of little tricks to make it balanced again. There are two popular strategies, AVL trees and red-black trees. I never really learned red-black trees. I tried to learn them later in life, and I was like, that makes no sense. I like the AVL trees. Basically, it's like these rotation strategies. We're not going to learn them. That's a 255. That's a next year problem. So self-balancing trees are an important thing, but we're not going to cover them. It's outside the scope of this course. But there are strategies like you could have like functionality built into your data structure to ensure that it's balanced and you're good to go, which I think is pretty cool. Okay. Any last questions before we move on to our implementation of a binary search tree? No? Everyone's happy? Everyone's happy. Good stuff. All right. By the way, I also fixed that link. Thank you very much. If anyone noticed, there was a link in the assignment where if you clicked comparator, it took you to comparable, which is not what I wanted it to. I wanted it to go to comparator. I don't know how that happened. I can guess how it happened. I just, can't read. But anyways, it has since been fixed. All right. All right. And if for whatever reason, when you go to the web page and you click it and it doesn't take you to comparator, it's because you didn't refresh your web page, and that's fine. It's because your browser is trying to be helpful in caching an old version of the web page. All right. Linked binary search. Let's make a binary search tree. Let's do it with a link structure because I like link structures. That's what we're going to do. And how are we going to do it? Well, start by making a class. Public class linked binary search tree. Then we have all that funny stuff in here again. And what's all that? Well, one sec. And then implements binary search tree. Binary search tree, we had like an interface that we defined the binary search tree, which itself inherited from binary tree, right? So, yeah.
We expected to know that it extends comparable question.
Oh, maybe. Now I'm wondering, I don't think that should be T. The binary search tree's generic type should also be T extends comparable super T, shouldn't it, right? Because the binary search tree's elements must be comparable. So I might have to go look at that. Anyways, if this is saying,
Maybe it's fine because in the binary search tree interface itself, it would define it probably as T extends comparable.
maybe?
super T.
Did we?
It's fine. I think we did. So I think it's like predefined, and that's fine.
Let me open it. Keep. Open. No, shoot. Don't open it in IntelliJ. Did I click it? See, that is a nice downloads folder, by the way.
It is.
You see that?
Yeah, Notepad plus.
Let's just go Notepad.
Offended by that statement.
Yeah, I see it.
You're it is there, yeah.
So I think it's fine.
But should it have been in the other place? Maybe it doesn't. I don't know. Whatever. You're offended by that statement? That's funny. Anyways, again, if you forget, what does all this stuff up here mean? It's a fancy way of saying, look, it's a binary search tree. It's generic, yes, but there's a restriction on the types that can be in there. The restriction is they can't be any type. It has to be a type that at least has a defined ordering. That's what this means. Okay? Cool. Right? So T extends comparable, and then what? Don't worry about it. It's got to be comparable, okay? Because the thing, like T and the thing it's being compared to don't necessarily need to be the same type, because what if something inherits from something, but it's still comparable? That's what that's kind of getting into. Don't worry too much about it. It's fine. I know, you're right. Yeah, but don't worry too much. It's like Java syntax too, right? So don't worry too much. All right. Public class, link, blah, blah, whatever. 2 fields, a size. So I guess we don't need a count method because we'll just know the size. Every time we add something, we update it. Every time we remove something, we update it. And we'll have a root, a node that references the root. And that's all we need because from the root, we can access everything, right? In the same way of like a linked bag, right? You only need a reference to the head of the bag. That's it. Linked binary search tree. The constructor, root starts null, it's empty. Cool. People have asked me, like, well, couldn't you make a constructor where you give it an element and then that adds it at the root? Yeah, sure, fine. You could do that if you wanted. Yeah. You could make one where you could make one where you give it a linear collection and it goes and adds all of those things in the correct order. For all I care, it doesn't really matter, right? You could do that. It's entirely fine. But for here, we'll keep it nice and simple. Any questions about any of this, what you're seeing right here before we carry on? Okie dokie. Now, we're going to do that private static internal class thing. We're going to call it node. The reason I like it to be private static internal is because, one, this node is important for the inner workings of this class. Yeah, other classes might need these like nodes that have two, but whatever. It kind of like, it's for this class. And also, I already like showed you an example of node being outside the class. So if you go look at my stuff, I've got a node class already. And I don't want to call it, give it a different name. I don't want to use a binary. And I just want to have a node. Otherwise, I'd have to give it another name, right? Because I'd have a name conflict. I have a class called node, which has for a linear structure, and a class called node for a binary structure. You could say, well, just give it a different name. I don't want to. I'm annoying like that. I just want to call it node. So there, I made it a private internal one.
Also makes your class more portable as well.
Exactly. Absolutely, it does. Because if I don't include it, then it's going to say, I'm missing a node. What's a node class? Well, if it's inside of it, it ain't going anywhere. What's that going to look like? Pretty straightforward. It's got some data left, right, a constructor, another constructor where you give it data to begin with. Get data, get left, get right, set right. So it's got accessors and mutators too. This is weird. A lot of people would say this is bad programming. Yeah, fine, whatever. For something like this, this is usually where people who are like really against side effects, this is usually where they go like, it's fine here. You know, it's like an internal one. You're fine. And then you might say, why not make these just public and then just modify these fields? Oh, sure, whatever. Do what you want. This is more of like it's an internal class that's there to help you make your data structure. I just like it this way. I like interfacing with classes through methods. Even if like it's just mutating and accessing some fields, fine. I like it that way, right? No, that's all. Things of note for this class. This is a binary tree node, thus it has a left and right. The nested static class is contained within this one, yeah. All right, now's a good place to end. I don't want to get halfway through any of these. Do we have any questions before we wrap up? All right, I'll see y'all later.